So, hello to our new part of the lecture. We will look a little bit more deeply into Bayesian modeling and inference for the next few lectures to come. And today we start out with the basic mathematics behind it and the introduction into the idea of probabilistic modeling and probabilistic learning, which is based on this Bayesian inference. So machine learning is typically based on data with one or more of the following properties. It's either stochastic or generated by a complex, non-deterministic, or not fully understood process, typically noisily observed or only partially observed, or even all of these at once. Probability theory is a wide field, as we are aware of. And typically it's focused on expressing modeling uncertainties in some way and finding some kind of appropriate data generating process. So a part of probability being applied for modeling and finding such processes is in probabilistic modeling, and probabilistic itself already contains the word probability in some way, and therefore it will be based on probabilities in some way. For those from the data science part, in unsupervised learning, there are some fields where we do not have an actual outcome data available for training an algorithm for doing back propagation in some way, and then introducing probabilities instead and not relying on deterministic decisions is an alternative approach. Among these things is naive Bayesian filtering, as applied, for example, for spam filtering of emails. Probabilistic models do not simply transform information in the data into single number outputs. So we do not just summarize data into a mean or a standard deviation, which are single number outputs, but instead of having just this single number as a summary, we want a probability about every possible value, which could be the mean of the data generating process underlying our observed data. And therefore, instead of just fitting a deterministic model, as we did before, when we were fitting regression lines, this was a single model with consideration of the noise part as the random residuals we were looking into there, but we considered these coefficients in a way as rather fixed and being best possible estimators, and just consider these single values as best possible as estimators. And now we will look at all these model coefficients in a quite different way. We will look at them as being inherently random, and therefore by treating them as random variables, we understand that they instead have probabilities and therefore also distributions of these probabilities. And we will want to learn about these distributions, and learning then is updating the information by the one observed in our data. To give you a little bit of an introduction into this, there is famous historical introduction for this. So Francis Bacon used the analogon of ancient Greeks and ships sinking in a storm or for other reasons, and the man going to sea, of course, believing in their gods, praying to Poseidon as the god of the sea, and hoping for this god to save them from drowning. And therefore, he proposed that the probability of survival, given that they prayed, was assumed by these people to be larger than the probability of survival would have been without any faith, without prayer. However, Greeks did not observe this probability of surviving given that they prayed hard enough to Poseidon, but instead they observed something else. Every single person who survived, as they were all like faithful believers of their god of sea, of course prayed to the god, and therefore this probability of this B given A is 100%. And they assumed, not having this strict context of probabilities and conditional probabilities as we have, that this would have been the other way around. So what we would like to learn about is the first type of probability and dependence or non-dependence. And this is what this whole notion of Bayes' theorem will be about. You might be more familiar with Bayes' theorem in its formulation for events, as we've written them before with our example of the seaman. This is the continuous way of formulating Bayes' theorem, based on some kind of underlying prior probability for a parameter, which is the pi of theta here, and a likelihood function, which is basically the data information given a certain parameter setting, given some parameter theta. Dividing by this, we will call it from then on the marginalization constant, the marginal distribution. And this will provide us with the information about the actual parameter theta, the actual choice of a mean, of a variance, of survival, given the data that we have observed. So the prior distribution is meant to introduce information which is available before our actual statistical analysis from any kind of external source into our model. This distribution assigns a probability value to every possible value of our parameter, which we a priori consider a proper choice for our current model. The likelihood function, as in all statistical models, which are based on some kind of likelihood, weighs how well the observed data fit to a chosen model for a certain choice of the parameter. This is what is optimized in classical maximum likelihood methods. And the dependence on the choice of parameter here is the relevant part. Otherwise, we would not have a link between choice of parameter and information in our data. So we would like to learn about this parameter based on our prior information and the information contained in our data. And this Bayesian approach has some advantages. For example, it also has a kind of regularization possibility, as we have gotten to know it through rich regression, that we could there also apply regression for somewhat correlated independent variables. Now we will have, however, a kind of different problem. We will have to choose two instead of just one distributions, not just the likelihood function, but we also have to consider the prior distribution choice. By combining those two sources of information, we will again end up with a probability of every single value, which might be appropriate or not for our model. And this is then the posterior distribution of probabilities. Why is this useful for learning for data science? Unlike the maximum likelihood approach or standard statistical approaches, which we have looked up until now, this allows us to merge the information from different sources of data as if they were the same source of data. This is called updating, and it works in the following way. We obtain a posterior distribution based on two different data sources, x1 and x2. And this is based on the likelihood, the joint likelihood, where data from source x1 and data from source x2, given the same set parameter theta with its prior, are considered. And we can split up, as the likelihood is just some kind of multiplication, into the part which is only dependent on source x2 and the part which is only dependent on source x1, and of course the prior part. And we can see when we only combine the information from source x1 with the prior, this is just applying what we've had before, Bayes' theorem, in this continuous case. And therefore, we end up with a posterior based on just the first part of the data. This posterior of the first part of the data will then become the prior for the next step of the data. And combined with the likelihood from source x2, we end up with a posterior which combines the information of both source x1 and source x2. So to visualize that and give you a little bit of better impression, as a prior, we have very vague information. Therefore, this red line, dotted red line, as we can see here, it's very widespread. With the first part of the data which we enter here, the information is driven into one direction, and we see the curve gets narrower and the peak gets a little bit higher. So now we have more information, more precise information, and we got a better direction where the mean in this case of this distribution may lie. And if we add another one, now the black curve is the prior, and then inferring again, we end up with the green posterior, which would have been the same thing as if we had put in both information things at one. So that leads us to considering advantages and disadvantages of this approach. All uncertainty is modeled as probability, and therefore the laws of probability are obeyed at all times. And with this Bayesian approach, we can therefore model hierarchical models with a lot of parameters simultaneously as a possibility. It allows us to incorporate prior scientific information from other sources. The appropriateness of this method is not depending on large sample sizes. Actually, it even works with a sample size of 0, because if I put in no data at all, the posterior will be identical to the prior, of course, because I learned nothing without any data, but still I obtain a full distribution of all my possible parameter values. So it works even without data, and in particular it works with very, very few data. We learn a lot from every single data point, but we can apply it for small and large sample sizes at last. Also, an advantage is that we can directly interpret these things as probabilities. You will probably have learned in previous lectures about how hard it is to interpret p-values properly, how hard it is to interpret confidence intervals properly, because their actual interpretation is not that this is in some way directly the probability of some value being correct, what everyone would expect. Now, this Bayesian approach has this direct probability interpretation, and therefore also prediction is straightforward from our models. However, this comes at a price. The price is, well, we can include prior information, but we have to include prior information. And the information we're including there, it will have an influence, of course, on our inference, in particular if we do it incorrectly. So obtaining these prior distributions for real scenario and this prior information might be somewhat tricky. We will look at some examples today, and also you in your exercises where you have reasonable prior information and you will try to include it in the data. Bad information is actually worse than no information. So giving it a wrong direction for our inference is worse than giving it none at all. And also we have the necessity of something called sensitivity analysis. This is something you will look into your second exercise, looking at the influence of the choice of prior and different parameter settings of your prior. So frequentist versus Bayesian analysis. This has been an ongoing battle in the 20th century, and it's still not decided. Both have their advantages and disadvantages. Whereas frequentist procedures are well established and well known, they depend on repeating the process that generates the data many times. This is this sample limit theorem idea. Whereas the Bayesian approach represents uncertainty through probability distributions. The frequentist approach is what comes to mind when one thinks of parameter estimation. There's a single value of this parameter. We don't know it, but we try to estimate it. Whereas Bayesian approach is, well, the parameters themselves, they're not fixed numbers in any way. They might be random in some way themselves, and they're still unknown, and we would like to learn about them, but we cannot learn about a single value. We don't just estimate a single value, we learn about every possible value. Frequentist estimation is unbiased. We've talked about bias before when we were looking at cross-validation. Bayesian estimation in itself is always biased. Just by considering a prior distribution, we put a bias on our estimation. We've also learned that lasso and ridge estimation is also biased compared to OLS estimation. But by introducing this kind of bias, we also get a kind of regulatory effect. So something similar is happening here with the Bayesian estimation. Because we introduce some kind of bias, in some cases, we end up with something more efficient than the frequentist unbiased estimator could ever hope to be. So with the Bayesian scenario, we make direct probability statements about our model parameters and the data, whereas frequentists' methods can only make probability statements about the data itself or data given the null hypothesis process, but not about the parameter because it's a single value. It cannot have a probability. Also, it's unconditional probabilities. We do not consider anything to put a condition on in frequentist analysis, whereas we always have conditional probabilities for a Bayesian analysis. So probability is the main difference here between the classical inference we've known up until now and the Bayesian statistical concept. This is also about being objective versus subjective. And this is a very philosophical talk, and we will not go into it in a lot of detail. Typically, because frequentist classical inference only considers the data itself and nothing else as an additional data source, it is considered to be an objective concept, whereas Bayesian methodology, because it considers, in addition to the data we observed, some kind of prior information, which is somehow subjective from the perspective of the researcher. This whole concept is considered to be subjective. So there are pros and cons. We will look at some of them for all the things we do from now on. And you should become aware of both methodologies at least. The likelihood function, as said before, just as a reminder, what it looks like. This is the product of the underlying probability distribution with the data substituted into it, given a certain set of parameter value, where it is this parameter value theta which we would like to learn about. So we will briefly revise the distributions which we have already looked into originally when we were looking at random number generation. I will not talk a lot about the different distribution functions, but I want to introduce you to some scenarios for which we select distributions. And we start out with discrete distributions. There's actual categories which we would like to model. So we have separate categories. We would like to have a distribution for how likely it is to observe any of these categories. And we can start out univariately with something like a uniform distribution if each category is equally likely to occur, just like rolling 1 to 6 on a 6-sided dice. However, if this thing is biased in some way, we would like to learn about it a posteriori in some way based on our data. Then there's indicators for groups. So being 0, being 1 in the dichotomous case, or being one of several group labels. In the first case, with just having 2 groups, we use Bernoulli or binomial distributions. In the second case, we use multinomial distribution with several underlying groups to choose from. And then there's count variables. Typically, those are modeled by Poisson processes or negative binomial distributions in some way. So as a reminder, or summing all these up, the uniform distribution, the binomial distribution, which we will use today for our example of deciding between 2 groups and having this P as the probability of success of falling into one of these groups. The hypergeometric distribution, which we will rarely use for Bayesian inference because the formula is just too complicated for inference. The negative binomial scenario with similar setting for priors as the binomial scenario, and also the Poisson distribution scenario. We will talk about those as likelihoods and priors later on. When I say we use them as a scenario for modeling data, then I mean that we use those things for the likelihood function of our model. Continuous distributions will be the easier things to use. So there are several ways where will require continuous distribution. One is really modeling continuous observations, obviously, as opposed to modeling categorical or discrete observations as we did before. For these, there are several types of scenarios. Of course, we are aware of the normal distribution being the thing to do when you do continuous modeling, because we have a mean, we have a standard deviation, we have two parameters of these distributions which are nicely and directly interpretable. However, there are some cases where this normal distribution will not be fitting. For example, skewed data. If these skewed data are at least of positive value, then we can try to apply a log normal distribution instead of a normal distribution, which means we'll use the logarithm on all observation, and what we would get out of these transformed values should then have a normal distribution. Or if this is not the case, if they're skewed and positive valued, but they do not allow us to use the logarithm for transformation, then we can still model gamma distributions in certain scenarios. This will be the thing to go. Remember, positive values, skewed thing, they can go up to infinity, but the lower limit will always be 0 or just above 0. Then we have the gamma type distributions. For bounded data, in particular data bounded between 0 and 1, the beta distributions will be the thing to do. Because the uniform distribution, the continuous uniform distribution, is a special type of beta distribution. I did not put it here separately. So beta distributions are for anything which is a bounded interval, which is a lower than clearly defined upper bound. And anything which is over dispersed and therefore diverging from this normal distribution setting will be modeled by heavy-tailed students' T distributions, for example. So this is modeling the data directly, but we need not only model the data, we can also model other things where we've already learned that there are distributions underlying. For example, anything that's a test statistics calculated out of things, or more in particular, residuals of models. When we looked at the linear regression scenarios, we were talking about the conditions and assumptions for the linear regression in order to apply. And among these assumptions was the normal distribution of the residuals. This normal distribution will now become our likelihood scenario for modeling linear regression, generalized linear regression, whatever else built on that, but also things like linear discriminant analysis. So the brief reminder of these distributions, and we will now learn about how to apply them as priors and what's useful about these things. So there's the natural conjugate prior concept of distributions, which means that the likelihood function and the prior distribution have a similar structure. What does similar structure mean? And I will now go back to the actual distributions. We look at the beta distribution, for example. Beta distribution is some kind of fraction, x to the power of alpha minus 1, 1 minus x to the power of beta minus 1. So this is the backbone structure, x to the power of something, 1 minus x to the power of something. Now we go back a little bit and look at the negative binomial, for example. This is also p to the power of some x, 1 minus p to the power of something else. It's again parameter to the power of something, 1 minus parameter to the power of something. This has the same structure, negative binomial distribution and the beta distribution. Parameter to power of something, 1 minus parameter to power of something. So this will be now of relevance for us when we talk about conjugate prior scenarios. We will look at these in two of our examples. And there is this Pitman-Koopman lemma, which guarantees that for a large enough sample size, there always exists a sufficient statistic of constant dimension for a family of distributions. Then this will be an exponential family of distributions, and we will always get a natural conjugate prior when we have a sufficient statistics. Elicited priors are the most difficult to construct ones. They are really manually putting weights on certain values of the parameter. They are most informative, but also something which is only existing for very specific scenarios. Then there's the non-informative prior concepts. There's the Jeffreys priors, the reference priors, and maximum entropy priors. We'll look into those next time when we do the actual modeling parts. For today, we will only focus on conjugate prior settings. So Jeffreys prior in its idea is to construct something which is invariant under diffeomorph parameter transformation. So we do not want the prior information to change if we transform the parameter. This is the idea behind the non-informative Jeffreys prior. The reference priors are linked to the asymptotic properties of the posteriors, whereas maximum entropy priors want to maximize the entropy in the sense of having the least information and the most prior uncertainty about the parameter by construction. So the important conjugate prior combinations for our likelihoods, our discrete likelihoods, will be binomial distribution data. We have two categories to put something into, and we want to learn about the parameter being the proportion of our success. Then this proportion of success will have a beta distribution. In the multivariate generalization of this, the multinomial distribution for our data, the conjugate prior will be the multivariate equivalent of the beta distribution, the Dirichlet distribution. We will look into those two a little bit more in detail when we talk about Bayesian semiparametrics and non-parametrics. The last scenario is the Poisson distribution. For this Poisson distribution, we have the underlying rate of an event occurring, and this underlying rate of the event occurring, which is the parameter itself, has a gamma distribution, which has the same structure as the Poisson. Then our most important thing, the normal distribution, of course, has conjugate priors, because normal distribution always has good qualities. The conjugate prior for the mean of the normal is a normal distribution again, which is really nice. The conjugate prior for the variance of the normal distribution is a so-called inverse gamma distribution, which means that instead of modeling the variance sigma squared, we could model its invert 1 over sigma squared and name this new parameter lambda. And instead of variance, we call this thing precision, because the larger the lambda, the smaller the variance, so it's more precise. And this precision parameter has a gamma distribution. And finally, having exponentially distributed data like survival rates of any kind, this underlying survival rate lambda again has a gamma distribution. So we will now look at a very simple example of body sizes, something where we can do this inference manually. And we will, for this time, start out just doing these things manually. We look at body sizes of humans, and our prior distribution is a normal distribution with a mean of 175 centimeters and a standard deviation of 14 centimeters. Then we have generated several observations, and if we fill these observations into the likelihood function, we will obtain different likelihood values based on the underlying parameter theta, which is the possible values of the mu, which is here at the x-axis, and the likelihood itself is on the y-axis. So we can see apparently there somewhere around 177 most likely is the maximum likelihood estimator. But now we're combining this idea of having the maximum of the likelihood function with the information we obtained from the prior, which has its mean as 175. So what to do? We start out with our prior distribution. We fill in the values of the mean and the standard deviation. And also we construct this likelihood function with our specific data xi. I color coded them for you to have it easier to follow these calculations. Basically, we drop the marginal distribution in all cases because it will only be a constant once we have observed specific data and put it in this marginal distribution. And we only need this constant in order to guarantee that the probability distribution of the posterior will have an area under the curve equal to 1, which makes it a probability distribution. So we combine the blue likelihood information with the red prior information, and we drop all these factors which only depend on the standard deviation, but which have no dependence of the mean mu in here. As you can see, the xi are the things we observed, and in the first likelihood part, there is mu, which is unknown, non-specified, and also in the prior part, there is the mu. So we want to reshuffle those calculations in such a way that we obtain the mu's by themselves and obtain something of the structure as we have in the third line here. We have e to the power of minus 1/2, and there is mu squared only multiplied by some factor. The first part stems from the likelihood, summing up n times something with a standard deviation or with a precision of 1 over 15 squared, plus the precision part of the prior distribution, minus the 2 times mu, and again we see the 1 over 15 squared, which is the precision stemming from the likelihood times the summed up data values minus 1 over 14 squared, again the precision of the prior with the prior mean basically coming in here. So we have n times the mean of the observed data coming into these calculations and 1 time the mean of the prior. And we weigh those two means by the precisions of the prior and the likelihood function. So we end up with something which is a combined precision of the observations from the likelihood, the blue part, plus the precision of the prior, the red part, the 1 over 15 squared times n plus 1 over 14 squared. And as a new mean, we obtain the original mean minus the mean of the prior, both scaled by the precision. So this leads us to this graphical inference result. We start out with the red prior, which is rather widespread. We learn through our data sample. We see the updating which happens here is the mean of the prior, which is the red vertical line, is moving to the right toward the information we would have obtained from the likelihood and toward the mean of the posterior. The actual maximum likelihood estimator would be somewhat larger than the posterior mean which we are observing here, because the prior has some kind of regulatory effect. As we can see, the larger this n gets, the more will be the influence of the data and the smaller will be the influence of the prior. So for n going to infinity, the prior influence will go to 0. And it simply doesn't matter anymore. So we now consider different informations which we can get from our posterior. We'll look at point estimation, we will look at hypothesis tests, we'll look at interval estimation. Not all of them today, but gradually moving in this direction. So relevant part for point estimators is that we defined some kind of loss functions. So as we have a posterior probability for every possible value of the parameter, we want to choose the value which minimizes a specific type of loss. And if we want to minimize the quadratic L2 loss for our posterior distribution, then we will obtain the mean of the posterior distribution as our point estimator. If instead we choose to optimize the absolute L1 loss, we do not end up with the mean, but instead with the median. And if we actually choose a 0,1 loss, which says I always lose except at the best possible value, well, then I will end up with the posterior mode as my best point estimator. This also leads us to the concept of highest posterior density intervals, which means we construct the shortest possible interval for a given coverage probability. What does this mean? It means, for our example with the body sizes, that we have the posterior mean and the posterior median and the posterior mode being the same value in this case, because it's a normal distribution as a posterior distribution. We see that since this is a posterior, of course, also the HPD intervals will be symmetric. And we obtain them in such a way that symmetrically we drop the highest and the lowest, like 2.5% or 0.5% for getting the 95% interval or 99% interval. If the distribution were not symmetric, we would have to look at these interval bounds manually. So this is the code for obtaining this. And now we also look at a second example scenario. This one is for spam filtering. We want to learn about the probability of an email containing a specific word being a spam email. So again, we will apply a Bayesian theorem in some way for every single word. And what we see in there, in order to be able to do this, we need to learn about the probability of some randomly selected email being spam. This is the basic of all these filtering algorithms for spam filtering emails. In reality, mail service providers know that this rate of spam emails is something like 80%. This is rather shocking. And the naive classifier assumes this to be fixed to 0.5. However, as you might have noticed, your email service provider gets cleverer if you manually select emails as being spam emails and manually classify them, because then it can learn based on your classification and do something much more clever than the 0.5 or 0.8 assumption, which is personalized to your mail account. And we will now look at how to use this and how to obtain inference about this. So in this case, we have only two options of something coming out of the decision. Either an email can be spam or it cannot be spam. So this is a 0-1 decision possibility. Therefore, the basic structure for this will be the binomial distribution, because if we have just one single email to classify, it's a Bernoulli scenario. If we have several emails to classify, then it will become binomial, and it will be the number of emails classified as spam emails, which we're inferring here. Therefore, underlying this is a parameter theta in the likelihood, which is nothing else than the probability of an email being a spam email. And therefore, 1 minus this thing is the non-spam emails. As we can see, we have y and then minus y as the information in the exponent, and therefore this has the same structure as something of a beta type distribution, where this alpha would be y plus 1 and beta would be n minus y plus 1. So now we learned how the likelihood is encoded. Even though it's a binomial distribution, we can transfer the information we have from our binomial distribution likelihood into a beta distribution scenario and also learn what the parameters would be, ignoring this normalization constants for the moment now. So now we want to assume things. We had 50 emails, and out of those 30 were spam up until now. So our faithful email client knows that there's 30 spam emails, 20 non-spam emails, which we've received previously. This will be our informative, so this will be our data. And now we would like to combine this with some informative prior scenario. The prior we've seen before on the rates of spam emails for this naive filter was 50% probability of being a spam email, 50% of being non-spam. This can be encoded as if we had had 10 previous emails, 5 would have been spam, 5 would have been non-spam, 50-50 chance. So this means that we can set this A to 5 and the B again also to 5, having equally weighted spam and non-spam emails as the previous scenario. With the 30 emails of our actual data, which were spam, and the 20 emails which were non-spam, and this 50-50 chance as a prior, we end up with a posterior, as we've learned. Everything that is in the exponent of the theta is the information about being a spam email. So the number of spam emails in our data, 30, will be added to the number of spam emails in our prior 5, which ends up with a posterior with a first parameter of 35. And also we sum up the 20 and the 5 to 25. This was simple enough. If instead we would use a different prior, because we can also get a 50% chance of something being a spam email, if out of 100 possible emails, 50 would have been spam, 50 would have been non-spam. Now the prior has much more weight, because you can see here, now it's 50 information from before, and we add the 30, the information in our data, ending up with 80. And we have the 50 information from before, and the 20, the information from our data, ending up with 70 as our second parameter. So this second scenario is the much more informative scenario, because the prior has much more weight as compared to the data. We can also see this here when we visualize the thing. In the first case, the prior contains much less information. We allow a lot more things as posterior, and therefore the posterior is more in the direction of where the data scenario would put it, because that would be 60%. So this posterior peak is just below the 60%, and the prior peak is of course at the 50% rate. In the second case, where the prior has a lot more information, we can see it's already higher and narrower, more information contained in the prior scenario, and the posterior shifts far less in the direction of the 60 as the mean. So we end up with something much smaller than in the scenario 1. If we look at the mode of this distribution, and therefore we see that here we have a more informative prior scenario, where the prior has more regulatory effect. It's more bias also, which is introduced as compared to the first scenario and to the maximum likelihood scenario here. So you will look into exactly that same type of scenario with your first type of exercise. You will also build a binomial distribution scenario. You will create a beta distribution prior. As we have just seen with the email scenario, you can directly interpret these exponents as the number of observations of a certain type of grouping. And in our case, we will look at the COVID-19 prevalence in spring 2020 and Then back then we had 1,279 persons being analyzed by PCR testing procedures and not a single person having been found to be tested positively. Whereas the prior information for this scenario will be that in Germany, out of 4,068 cases, 4 cases were tested positively. Therefore, in a similar way as we did here, you can construct the prior and based on this, the posterior distribution. And that's exactly what you should do. I showed you what happens if you reweight the parameters with a factor of 10 in my scenario here in the lecture. You will, instead of multiplying by 10, divide by 10 in order to make it less informative. Then you should also obtain the posterior distribution for this scenario and the point estimators for this posterior beta distribution and the HPD interval for this case, and explain why Statistik Austria chose exactly this kind of method and approach for estimating the prevalence of the disease in Austria instead of any other simulation-based or frequentist inference approach, because all the others failed. Task 2 will be to revisit linear models and residual distributions. As I said, linear models have a normal distribution for the residuals, and the mean of this normal distribution is, of course, the value of the estimator, the X transpose beta, and the variance of this normal distribution will be the residual variance, the sigma squared. And based on these, use from the conjugate prior table you've been given above, the construct conjugate priors for this beta parameter, and for the residual, not means, but variances independently, and explain what in this case you would have to do to make them not informative as we have had it in our examples here, but to make it rather uninformative. What to do to reduce the amount of information introduced by the prior. In order to give you a direction, compare what scenario 1, which is less informative than scenario 2, has as a defining quality for its prior distribution, and try to make this more pronounced with the construction of your priors. So based on these, define the posteriors for a general linear model construction, and how to obtain point estimators of the coefficients and the residual variance, and how to obtain the 95 highest posterior density interval for this scenario, and then reuse the data which you've already used in exercise 6, this MPG versus horsepower from the auto data set, because there you already estimated once the linear model with the classical OLS estimator, and now you should compare it against your Bayesian results for the 3 different prior for the different parameter choices you have as a prior parameter selection. Comparing these different prior choices against a classical thing and against each other is what is referred to as this type of sensitivity analysis. Good. So much for this week. Um, I hope you will have some fun with that. Good luck with it. And if you have questions, I will be available again on Tuesday for our lecture time.